structure, okay? And then, yeah, we'll decide kind of when we'll have a quiz full, okay? And then in the end, okay, so yeah, probably we'll have some time left, okay? We'll start a new chapter, chapter 7, okay? And again, so if you have any question, okay, so please type in the chat window, okay? All right, okay, so before we start kind of learn the ring flipped structures, okay, just keep in mind, okay? So yeah, you can write it down, okay? So yeah, when you draw ring flip structure, and always the equatorial bond become axial bond become equatorial, okay? So these two kind of the change, okay? So yeah, during ring flips, okay? So go back and forth, okay? But the pointing, okay? Pointing won't change, okay? Pointing means the going up or going down, okay? So yeah, if it's kind of the up, okay, after ring flip, okay, it's still up, okay. So if it's the down, okay, so it's also going down, okay. So yeah, pointing won't change, okay. So that's kind of critical, okay. So yeah, please write it down. All right, so now we go back here, okay. So we start can talk about the monosubstitute cyclohexane, okay. So yeah, when you do ring flip structure, okay, so there are two possibilities, okay. You can one is put this monosubstitute group K in the equatorial position, okay. So we'll do ring flip, okay, and then another kind of put in the axial position, okay. And so last time we learned that, okay, so the axial position is not stable, okay. There's a 1,3 diaxial interaction. That's kind of the static string, okay. And so they're too close to the two axial kind of hydrons, okay. But if you put this monosubstitute group okay, in equatorial position, okay, and there's kind of a lot of space available for it, okay, so that's much more stable, okay. And so in this case, most time, okay, so 95% time, okay, so for this methyl cyclohexane, okay, you stay at kind of equatorial positions, okay. Y and X axial. Has nothing to do with the Y and the X axial, okay. So I will talk about more, okay. So don't worry, okay. So yeah, how do you draw ring flip structure, okay? Yeah. All right. Okay. So yeah, if it's the more bulky group, okay. So for example, the turbulent group, okay. Yeah. Yeah. So ring flip is just kind of a different conformation of one cyclohexane, okay. So yeah, so I will show you more structure later, okay. Don't worry, okay. So yeah. Okay, so yeah, for example, turbulent group is kind of too bulky, okay. And in this case, 100% time, okay, you have to put your turbulent group at equatorial positions, okay. And impossible, do ring flip, put the turbulent group in the axial position, okay, because they're kind of too crowded, too close to the two axial hydrons, okay. And so then, we call this turbulent group as the anchoring group, okay. Anchoring group, what that means? That means kind of once you have this very bulky group, okay, so you cannot do any ring flip, okay. So the only conformation you can keep is just put your turbulent group in the equatorial positions, okay. Right. So here the first conclusion, okay. So yeah, if it's monosubstitute substitute group, okay. Monosubstitute cyclohexane, okay. So yeah, always you want to put the substitute group, okay, in the equatorial position, okay. Equatorial position, okay. So yeah, and that's much more stable, okay. And then most time kind of will stay at kind of equatorial position, okay. So write it down, okay. All right, and then comes kind of situation, the more than one substitute group, okay. So we do the first kind of disubstitute cyclohexane, okay. So for disubstitute cyclohexane, there are kind of two possible, actually more than two, okay. So isomers, okay. One is two group on the same side of the ring, okay. So that's what we call the cis, okay. Another we call kind of trans, okay. So one going up, one going down, okay. And here's kind of the cis 1,2-dimethyl cyclopentane. This one's the trans yeah, 1, 2, yeah, dimethyl cyclopentene, okay. Those two are actually kind of the pair of the stereo isomers, okay. And so yeah, for the cis, okay, actually you can also draw like this way, okay. Yeah, that's here 2 dash bond, okay, that's the same thing, okay. And there are also other way to draw the cis trans isomers for the disubstituted cycloalkene, okay. And so first is yeah, draw like something like this. Right. So the two bond going down, okay, that's indicate kind of these two group kind of going away from you, okay. So maybe draw your trans, okay, you can do some kind of comparison. Right. So that's trans, okay. So if you draw this kind of structure, okay, so that will be like this, okay. Yeah. Okay. So those are two same thing, okay. And then third way to draw the alkene kind of substitute cycloalkene, okay. So yeah, you more close to is the real structure, okay. So yeah, for cyclopentene we know that kind of the in envelope structure, okay. Yeah, something like this. Right, and then one going up, one going down, okay. So here, this one should going down, okay, and then another one, okay, somehow kind of going up, okay. Okay, something like this, okay. And then for this one, okay, so yeah, both kind of going up, going down, okay, so yeah, it should be like this. Okay, so that's another way to draw it, okay. So yeah, make sure you understand they are kind of actually some same thinking. All right, okay, so yeah, when we come kind of reflip structure for disubstitute the cyclohexane, okay, the situation gets more complicated, okay. So we first talk about two subgroup same size, okay, so same size, okay. And then also really depends the two subgroup kind of the 1, 2, 1, 4 or 1 3 kind of position of cis trans, okay. So that's the situation can get very complicated, okay. And here we use the 1,3 dimethyl cyclohexane as example, okay. So 1,3 dimethyl cyclohexane can be in trans, also can be in cis, okay. So we do the cis first, okay. So now cis kind of both subgroup, okay, on the same side of the ring, okay. And then we'll do ring flip, okay. So yeah, for the 1,3 the cis dimethyl cyclohexane, okay, can have two conformation, okay. One conformation, okay, so the two methyl group will both in equatorial positions, okay, so kind of in equatorial position, okay. And another conformation, okay, when you do the kind of ring flip, okay, both will be in axial positions, okay. So definitely kind of this diaxial, di-equatorial position kind of more stable than kind of this axial kind of positions, okay. So yeah, because this one, two bulky group, okay, both the point into last steric hinge kind of positions, okay. But yeah, when we come to the trans, okay, so the 1,3 dimethyl cyclohexane, okay, the situation kind of a little bit different, okay. Right, for trans, okay, so the one conformation will put one methyl group in equatorial and then one methyl group at axial, okay. When you do reflip, okay, so equatorial become axial, axial become equatorial, okay. So you still get the one methyl group at axial, one methyl group at equatorial, okay. And in this case, for these two, reflip structure, they have same energy, okay, because always one at equatorial, one at kind of axial, okay. And so depends what kind of situations, okay. So cis trans, okay, so when you compare that kind of energy, okay, so they may have difference, okay. So for example, this 1,3 dimethyl cyclohexane, okay, the cis conformation is more stable than trans, okay, because the cis you can put the two methyl group at equatorial positions, okay. And then the trans always has one equatorial, one axial, okay. So that's the cis overall has a little bit lower energy, okay. So more stable than the trans isomers, okay. Okay, so for other kind of disubstitute kind of for other kind of the dimethyl the cyclohexane, okay, so 1, 2 and 1, 4, okay. So maybe different situation, okay. So really depends kind of the real case, okay. And you have to analyze individually, okay. So those maybe not true for here, okay. So to give you one example, okay, so you will understand what I mean, okay. For example, okay, so we use the 1, 4 example, okay, 1, 2, okay. 1,2 disubstitute the 1,2 dimethyl cyclohexane. Okay, so this is the cis. Okay, and then we also draw trans. Right. Okay, so we'll do the reflip structure for individual one. Okay, so here I just quickly draw it. Okay, and then later we'll come back kind of show you guys kind of how to draw reflip structure. Okay, so don't worry. Okay, so you'll come back later. So reflip structure, keep in mind. Okay, so mirror imaging to each other. Okay, and you need to find the corresponding the carbons. Okay, so corresponding carbon, this one, this one. Okay. Okay. So because it's the cis. Okay. So right. So these two wedge bond indicate kind of point up. Okay. So point up. Okay. So for this carbon, okay, point up bond will be axial. Okay. For this carbon, point up bond will be kind of equatorial. Okay. And then when you do reflip, keep in mind. Okay. So I just showed you before. Okay. So you want to change the equatorial to axial. Won't change kind of up down. Okay. But you change equatorial to axial, axial to equatorial. Okay. So here, okay, so axial become equatorial, okay, but still point up, okay, and then here, the axial kind of equatorial become axial, okay, also point up, okay, so all right, so that's this two, okay, and if you analyze the other kind of energy, okay, so these two should be same thing, okay, because they're one equatorial, one axial, okay, so those two kind of same, okay, all right, and then when we come kind of the trans, okay, the trans, we do the similar thing, okay, so try to draw they're kind of the mirror imaging, okay. All right, and then we still do these two carbons. All right. Okay, so now it's kind of one going up, one going down. Okay, so we do this carbon first. Okay, so that's correspond to this the dash bond. Okay, so that's going down. Okay, so it's going down. Okay. And then this one kind of going up. Okay, so that's the match bond. Okay, so that's going up. Okay. Yeah. And then when we do reflip, okay, so the equatorial become axial, axial becomes equatorial. Okay, but the pointing won't change. Okay, so this one going down, still going down. This one going up, still going up. Okay. Okay. All right, and then afterwards, okay, so we'll analyze analyze kind of stability of these two compounds. Okay, you'll find the one conformation can put two groups in equatorial positions, both in equatorial position, but another one will put both in the axial positions. Okay, definitely kind of this one is more stable. Okay, so that's okay, and then if we compare it with this is 1,2, okay. 1,2 dimethyl cyclohexane, okay. So with the 1,3 dimethyl cyclohexane, you find kind of a little bit different, okay. So for the 1,3, okay, cis is more stable than trans. Cis can put the both methyl group at equatorial position, okay. But for 1,2, okay, trans kind of more stable, okay, because trans you can put both methyl group at equatorial equatorial positions, okay. So that's means there's the hard to see kind of a certain rule, okay. So depend really kind of your situation and then what kind of your relative positions, okay. Cis trans, okay, you have to do individual analysis, okay. So all right, so that's for the two same suction group, okay. Now if the two groups are different, okay, so especially the two different sides, okay. So how's that any kind of different kind of reflex structure? The answer is yes, okay. Right, we use this molecule as kind of example, okay. So still the disubstitute the cyclohexane, okay. So yes, you can put the double bond in the chair conformation, okay, but that's beyond our class, okay. So if in future you take advanced organic chemistry, okay, so there's the chair conformation can have a double bond, say double bond, okay. All right, okay, so for this one, okay, so we have one phenyl, one methyl group, okay, one full position in the trans. And so the phenyl is kind of a much larger size because that's kind of another 6 membrane, okay. Okay, so for if it's kind of in the trans, okay, so again you can do the reflip, okay. So one conformation you can put the both sucking group at equatorial positions, okay. So that is more stable one, okay. Another conformation, okay, so probably quickly draw you guys, okay. we'll put kind of both at the axial positions, okay. Yeah, say 3 and then 3 will be here. Okay, so that's here you kind of extremely unstable, okay. So for this situation, kind of pretty easy, okay. So easy identify, okay. So yeah, that will be kind of a more stable chair conformation, okay. So yeah, stable by 1.7 kcal per mole, okay. All right, but when we come to the cis, okay, so here's the trans, okay, and cis here means here both here the substitute group will be on the same side of the bond, okay. So yeah, for this case, kind of bonds point up, okay. And then we'll do reflip, okay. So yeah, always put one group at exterior, okay, always, and then equatorial and axial, and then put another when you do reflip, okay, put another one in equatorial and also axial, okay. Always one equatorial, one axial, okay. So which one is more stable, okay? So yeah, this one is kind of this one, okay. The last one the most stable, okay, because this one can put a more bulky group at the equatorial positions, okay. And then that's stabilized by, you can see compare kind of the string energy, okay. So last one kind of 1.7, right one kind of 2.9, okay. Last one more stable, okay, because you can put more bulky group at the equatorial positions, okay. Right, and then now we come kind of the rule number 2, okay. Here, so the rule number 1 for the mono substitute kind of the cyclohexane, okay. So rule number 2, okay. So if we are 2 groups, okay, or more, okay, so actually kind of more than one 2 group, okay, so that's fine, okay. If 2 or more substitute group, okay, really depends what size, okay. So if we are same size, okay, same size substitute group, okay. So yeah, you want to put more substitute group, okay, in equatorial position, okay. Equatorial. The more the chair conformation, you can put more subgroup in equatorial position. That's the most stable, okay. But if they are different size, okay, different size, okay, then you want to put a more bulky one in equatorial position, okay. Yeah, so that's rule number 2, okay, more bulky one, okay. So why is kind of the more stable at the equatorial positions, okay? Because the last year we learned in this slide, okay. Yeah. So yeah, the more bulky group, okay. So yeah, if we use equatorial position, okay, there's no atom around it, okay. So there's no steric string, okay. But if it's kind of in axial positions, okay. So yeah, there's 1,3 diaxial interaction, okay. Very strong kind of the steric hindrance, okay. So 1,3 diagonal steric hindrance, okay. So that's kind of the last stable, okay. So that's the reason, okay. And especially true for the bulky group, okay. So yeah, if you put a bulky group at the axial positions, okay. So for example, the TBO, okay, too crowded, okay. So impossible, okay. So yeah, in the axial position, you have to put bulky group at axial positions, okay, equatorial positions, sorry, okay. All right, yeah, that's general case. So yeah, the conformation will more groups, okay, large group in equatorial position, okay, are stable, okay. So it's stable, okay. So yeah. Right, and then here kind of we'll learn how to draw the kind of chair conformation from wedge dash structure, and also how to do the kind of reflected structures. Okay, so yeah, and take out your the pen and also get kind of paper. We'll do kind of little by little. Okay, and the first you okay just keep in mind, okay, so yeah, if the wedge dash structure show the wedge bond, okay, so yeah, that's indicated this bond is going up, okay. Okay, so for example, this is wedge bond that's going up. Okay, so if it's kind of dash bond, it indicates this the bond is kind of going down. Okay, and so wedge dash has nothing to do with kind of equatorial axial. Okay, because they will do reflip. Okay, so equatorial become kind of axial will become equatorial. Okay, so that's please keep in mind. Okay. All right, and then most common question kind of is I gave you one that structure as you kind of draw two reflipped structures. Okay, so two chair conformations. Okay, I can indicate which one is kind of more stable one. Okay, all right. So for these type of questions, okay, so probably get a new paper. Okay. Yeah, do it stepwise. Okay, so first I will kind of label the carbons, okay, number the carbons, okay. So for example, we still use this one as example, okay. So for the number of the carbon, okay, it doesn't matter, okay. So you can do clockwise, counterclockwise, okay, and those from any carbons, okay. No necessary kind of the same as the nomenclature. Nomenclature you have to kind of from the highest particle group. This one doesn't matter, okay. So whatever you want, okay. Yeah. All right. For example, okay, I start with this carbon, do the clockwise, 1, 2, 3, 4, 5, 6. All right. Okay. And then go ahead and draw two chair conformation in mirror imaging, okay? So that's what we learned last time, okay? So two chair conformation, okay? Yeah, mirror imaging to each other. And then following come to an important part, okay? Try to numbering these two chair conformation, okay? All right, keep in mind, okay, so this time we'll number it, okay? So top one's kind of turbulent, okay, turbulent, okay, yeah, not isopropyl, that's the one last carbon, okay. All right, okay, so we'll number it, okay, so doesn't matter from which carbon, any carbon will be fine, okay. But more important kind of make sure they are in the same direction, okay. So for example, I numbered kind of in the clockwise, okay. So when you number these two guys, okay, also do the clockwise, okay. And also, for these two chair conformation, you have to mark the same kind of corresponding positions. Okay, don't do a mirror image. Okay, all right. So for example, okay, so for this one, okay, so let me try. Okay, so let's try to number from this carbon. Okay, that's carbon 1, and then we do kind of clockwise. Okay, 2, 3, 4, 5, and then 6. Okay, all right. Okay, so because we start from this carbon, okay, so its corresponding carbon should be here, okay, so that's 1, okay, right, so this is 6, okay, 1, 2, 3, 4, 5, and 6. All right, okay, so make sure that same positions, okay, don't do mirror imaging, and also do the same directions, okay. All right, next, okay, we can add the bond, okay. So for this molecule, okay, so we have subgroup on the carbon 1 and carbon 3, okay, carbon 1, okay. So for you guys, okay, so my suggestion kind of just put the 2 bond on, okay, so otherwise you either got confused, okay, so both equilibrium axial bond, okay, so okay, so for the put 2 bond on, okay, so for the carbon 1, this carbon kind of point up, okay, that means the axial bond should be going up, okay, and then equilibrium should be going down, okay, so parallel to this bond, okay. So carbon 3, okay, so this bond can also, this carbon also point up, okay, that's the axial bond point up, okay. Equilibrium bond will be pointed down, okay, parallel to this bond, okay. All right, so once you get these 2 bonds, okay, and then you look at kind of original kind of the structure, okay. So here, okay, so that's the wedge bond, that means here going up, okay, so that means here isopropyl should be this one, and here should be hydrogen, okay. And for this one, okay, that's going down, that means kind of dash bond going down. So this means kind of this is your methyl group, okay, so methyl, okay, and then this one should be hydrogen, okay. And then next kind of we do the same thing for the carbon 1 and the 3, okay, so on the mirror imaging one, okay. So carbon 1, okay, so better put the 2 bond on it again, okay, and then carbon down, okay, so that's been kind of axial going down, equilibrium going up, okay. Carbon 3, same thing going down for the axial, going up for the equilibrium, okay. Once you have these 2 bonds, okay, go ahead, okay, so add the turbulent and also methyl, okay, turbulent, okay, so still going up, okay, so that should be this here, and then hydrogen we'll see here, okay, and then for methyl, okay, so that's here, okay, going down, okay, and hydrogen here. All right, okay, so that's how do you convert the wedge structure into the 2 chair conformation, flipped one, okay. All right, here's a question for you guys, okay? So which conformation is more stable? Okay, so left one or right one? Okay. which conformation is kind of last string, okay? Right, so yeah, you can type the answer in the chat window. Yeah, that's right, okay, right, okay, so all right, okay. This is the most stable, okay, the reason for that, okay, so yeah, we have two group, different size, okay, one's turbulent, one's the other mass, okay. Turbulent definitely kind of much bigger than the mass group, okay. And so in this case, yeah, we want to put turbulent at the equatorial position possible, okay. And this, right here, the conformation kind of we put the turbulent in equatorial, okay, that's the most stable, okay. Yeah, good. And here's just a rule I already talked about. Okay, so if it's same size subgroup, okay, so you try to put as many as possible. The subgroup in equatorial kind of more stable. If different size, okay, try to put a big subgroup, okay, at equatorial positions. Okay, so that's this case. Okay, all right. Okay, so now So in the discussion, yesterday, okay, so we have one question left not answered. Okay, so this one, okay. So as you kind of draw the ring flip structure for this molecule, okay, and then identify which is the more stable, okay. Right. Okay, so you guys take try for this this question, okay. If someone like you can also turn the annotation, okay, and then draw the two chair conformation, ring flip structure for this molecule, okay, and in the screen, okay, on screen. This morning section, okay, there are some students that did it, okay, so pretty good, okay, draw the two chair conformation on screen, okay, and then label all the bound kind of right, okay, so and for this afternoon section, okay, so if someone want to take a try, okay, so you can also draw the two chair conformation on the screen, and then mark all the substitute group, okay, and then also kind of label which one is more stable, okay, take a try, okay, so no problem, okay. Anyone want to take? Okay, so I saw one black line. Okay, go ahead. Okay, okay, don't worry. It's not easy. Okay, so draw kind of on the screen. Okay, so but just try your best. Okay. Or anyone want to take a try? Okay. First step, okay, that's right, okay. Draw the two chair conformation mirror image into each other, okay. That looks like a very nice one, okay. And then second step, okay, so you add a second substring group, okay, so Okay, that's good, okay. That's two chair conformation in mirror imaging, pretty good, okay. So now add the substring group, okay, please, substring group, okay. All right, so we have the two methyl group, okay, and then one ethyl group, okay. So that's the hard one, okay. Okay, that's right, okay, hydrogen, okay, got it. All right, that's hydrogen with ethyl, I guess, okay. Ethyl going down, that's right, okay. All right, so this going up, okay, so that's pretty much, okay, that's pretty much is right, okay, so go ahead, draw the another one, okay. Other student can also please practice on it, okay. So we'll have some similar question in quiz 4, okay. So ask you kind of I give you one structure, okay, ask you convert it to chair conformation and do the ring flip, and then show me which structure kind of more stable. Okay, so this unfortunately, okay, so the basic technique you have to learn in organic chemistry. Okay. All right. Okay. So that's no bad. Okay. Okay. Go ahead and draw another two substitute group. Okay. All right. Good. Okay. No bad. No bad. Okay. All right. So which one is more stable? Okay. You can put some kind of circle or arrow. Okay. So yeah, label most stable one. All right. Good. Okay. Pretty good. Okay. All right. Okay. So only two small problem. Okay. So yeah, the first. Okay. So this carbon. Okay. This carbon point down, okay, so that means here the equatorial bond should be going down and the axial bond should be going up, okay. So yeah, the methyl should go in this way and then hydrogen going this way, okay. And then for here, okay, so yeah, the same thing, okay. So yeah, this carbon going up, okay. So that means methyl going up and then hydrogen should go like this way, okay. So equatorial, okay. But overall, that's pretty good answer, okay. So especially you guys kind of just start to learn how to draw just start to learn how to draw the kind of draw the kind of chair conformation. Okay, all right, okay. So here, just again, okay, quickly show you guys kind of how to answer this question. Okay, all right. So pretty good. Okay, draw kind of mirror imaging for two chair conformation. All right, okay. And then you can go ahead and number it. Okay, so doesn't matter. Okay, which carbon do we want to start? Okay, 1, 2, 3, 4. Okay, so clockwise. Okay, so this time. Okay, so I'm going to start number from this carbon. Okay, so 1, 2, 3, 4, 5, 6. Okay, all right. Okay, so keep in mind. Okay, so for its mirror imaging, you have to start from same carbon and the same direction. Okay, 1, 2, 3, 4, 5, 6. Okay, all right. So next, okay, we can add bond. Okay, so for this method, that's here the wedge bond. Okay, that's going up. Okay, so let's see. Okay, again, okay, so for you guys, okay, so the student kind of show the structure on the screen. Okay, pretty good. Okay, so he or she kind of draw the two bond. Okay, so you should also do so. Okay, so this carbon going down. Okay, so that's here the axial. Okay, going down and equatorial going up. Okay. And then for 2, okay, so this carbon going up, okay, axial going up, okay, equatorial bond going down, okay. And then for 4, okay, so the carbon going up, okay, so axial going up, equatorial bond going down, okay, so parallel to here, okay. All right, so now we add kind of which, okay, so methyl, okay, so that should be kind of going up, okay, this will be hydrogen, and then for here, okay, 2, okay. Ethyl is kind of going down, okay, so that's goes here, and then hydrogen going up, okay. For 4, okay, so methyl is going up, okay, and then hydrogen going down, okay, so that's we added it, okay. We do same thing for this, reflect structure, okay, and then when you do reflect, okay, so equatorial become axial, axial become equatorial, but pointing won't change, okay. Carbon going up, okay, so axial going up, okay, and then carbon going down, axial going down, equatorial going up, okay. And then carbon going down, equatorial going up, axial going down. All right, okay, so now we add kind of methyl ethyl whatever, okay. So for carbon 1, okay, so won't change kind of pointing, still going up, okay, and just change equatorial to axial, okay, and then same thing for here, okay, so won't change pointing and just ET here and then hydrogen here, okay, and then this one methyl here and then hydrogen here, okay, so pointing won't change up, okay. Going up, going down, going up, okay. Going up, going down, going up. Same thing, just equatorial become axial, axial become the equatorial, okay. All right, and then ED analyze, okay, so that should be more stable, okay, because this one you can put 2 methyl and also the methyl and also equatorial. Maybe label this guys. So for here, okay, so we put the ethyl group at equatorial, methyl also at equatorial, only one methyl at the axial position, okay. And here, methyl at equatorial, actually at axial, okay, axial, ethyl also at axial, only one methyl at equatorial, okay. So definitely this is more stable, okay, because yeah, we can do the two cyclic group at the equatorial position, okay. So it's more stable, okay. Pretty good, okay. All right, okay. So that's we done the chapter chapter 6, okay. Chapter 6 actually kind of not too much material, okay. So only 3 components, okay. So one is kind of the arcing kind of easy cis trans isomer, okay. Cis trans, okay. So yeah, make sure you know how to assign the cis trans of the isomer for the arcing, okay. So that's relatively easy, okay. Second one is kind of the conformation of the saturated cis single bond, okay. So this one you should able to convert that structure into a Newman projection, okay. And then you should able to kind of rotate or general kind of several conformation of the Newman projection, okay. So just rotate one carbon, okay. And then just keep in mind more stable one, okay. So should be the two most bulky group kind of in anti-positions, okay, 180 degree, okay. Least stable ones kind of the two bulky group and kind of eclipse together, okay. So kind of overlap to each other, okay. So those are least stable one, okay. Yeah, so probably will have kind of similar question in the quiz, okay. So ask you kind of draw Newman projection and then analyze which is the most stable, which kind of least stable, okay. And the last kind of topic just the cyclohexane the chair conformation, okay. So you're able to do the ring flip, okay. Yeah, so that's only these 3 topics, okay. And so because for chapter 3, okay, so the lot of drawing, okay, so especially kind of the chair conformation, ring flip, okay, and also Newman projection, okay. So I decided kind of for chapter 3, okay, for the quiz 4, okay, quiz 4 cover the chapter 6, okay. Quiz 4 we will do it the paper-based quiz, okay. So you have to draw the real chair conformation to ring flip and the Newman projection, okay, by hand, okay. So if we do kind of paper-based the quiz, okay, so we'll do it in the class time, okay, and pretty much during the class, okay, so we have the 15 minutes class time, okay, and so probably first 20 minutes, okay, I will give you guys kind of just continue the lecture, okay, and then leave like 30 minutes for the quiz, okay. So normally speaking, I just post the quiz on EduCat, okay. You guys just kind of download it, okay. So you can print it out, okay. So if you don't want to print it out, that's fine, okay. Just write your answer on kind of blank paper, okay. And then after 30 minutes, okay, and then you just take a picture of your the answer, okay, and then upload online, okay. I will open a kind of Dropbox on EduCat, okay. Just upload the answer online, okay. So that's what we'll do in this way, okay. And then here a question for you guys, okay. So so we can have a quiz for either in Monday's class or kind of in Wednesday class, okay. So if you want to, you want more time to study, okay. So we can put it on kind of Wednesday class, okay. And here's the poll for you guys, okay. Some students already voted, okay. And so just vote, okay. So when do you want to take quiz 4, okay? So in the Monday class or in Wednesday class, okay. Right, and then give you the 3 more seconds, okay. 3, 2, 1, okay. All right, so similar like this morning class, okay. Majority students want to take the quiz in the Wednesday class, okay. That's fine, okay, no problem, okay. And so but just keep in mind, okay, because we have 2 lecture sections, okay. So the Monday class, okay. So I mean the Wednesday class, the morning one, okay. So we have a different quiz, okay. So I have to prepare 2 different quiz, okay. One is for the morning class, okay. One is for the afternoon class, okay. All right, thank you guys, okay. So keep in mind, okay. So Wednesday class, we'll have the quiz 4, okay. And all right, okay. So that's we done the chapter 6, okay. Any questions? chart window. Oh, here. Right. So if there's no further questions, okay, so yeah, we'll start the new chapter today, okay. Okay, so yeah, that's chapter 7. Okay, so yeah, chapter 7. Frankly speaking, okay, I will say that's the most kind of difficult chapter in organic chemistry 1. Okay. And because we'll talk about a lot of the stereochemistry case, so if you have a good 3-dimensional imagination in your mind, okay, that's maybe relative for you, okay. And so but for some students, okay, so this chapter maybe is your nightmare, okay. And so I will try to slow down in this chapter, give you guys a lot of example, okay. So if you get confused, okay, so you can stop me anytime, okay. So just kind of typing kind of I cannot follow you. Why is that? Okay, so I cannot imagine it. Okay? That's no problem. Okay, just stop me, okay. And just one thing keep in mind, okay, so don't miss any class, okay. So if this lecture, okay, so if you miss class, okay, so sometimes kind of hard to catch up, okay. So hard to catch up, okay. And for example, okay, on Monday we have the no quiz, okay, something kind of maybe you think kind of don't need time, okay, but maybe you miss some kind of important point, okay. Some on Monday I'll cover some kind of most important material, okay. So for chapter 7, okay. All right, okay, let's start, okay. So we already learned about isomers, okay. Isomer are kind of compound, okay, with the same formula, same number of carbon, hydrogen, or oxygen, okay, but actually different compound, okay. So we already learned 2 types of isomers. One is the continuous isomer, okay. Another stereoisomer. Continuous isomers is the different connections, okay, different position of a certain group, okay. For example, these 3 molecules, okay. So O are say 3H6O, okay. So the formula, okay. And then you can see kind of CO double bond kind of at different position of the carbon chain, okay. And last one just kind of totally kind of different connectivity, okay. So those we call the continuous isomer, okay. For stereoisomer, okay, so another kind of so that's the same connection, okay, same kind of the carbon double bond or whatever connection, okay, but different kind of spatial arrangement or kind of different pointing, okay. So for example, okay, so we have the cis trans isomer, just learned kind of belongs to stereoisomer, okay. So cis isomers, okay, so has 2 alkyl group, okay, on same side that bond. Trans isomer has 2 cyclic group, okay, on the opposite side that bond, okay. So that's we already learned, okay. And actually for the stereoisomer, there are also many other types of isomers, okay. So including the enantiomers, okay, and the diastereomer, okay. So cis trans isomer actually is one type of diastereomers, okay. We will learn other diastereomer in this chapter, okay. So for chapter 7, we mainly focus on the enantiomers and also the diastereomers, okay. So okay, so first we have to know what's the enantiomer, what's the diastereomer, okay. Right. So for the enantiomer, okay, so that's the 2 stereoisomer, has to be stereoisomer first, okay. They are non-superimposable mirror imaging to each other, okay. So what's that mean, okay? So first these 2 molecules has to be mirror imaging to each other, okay. So and second case, non-superimposable. Non-superimposable kind of connote the old atom match each other, okay. So that's non-superimposable, okay. And then once you understand what's enantiomer, okay, that's the following is pretty easy, okay. So the definition for the diastereomer, okay. Diastereomer is kind of the first they have to be the stereoisomer, okay. Second, okay, as long as these 2 stereoisomer, okay, not enantiomers, okay, then these 2 atom, okay, 2 molecule will be diastereomers, okay. So that's kind of important, okay. So that means kind of the not mirror imaging and also non-superimposable, okay. So stereoisomers, okay. And then here we will learn the enantiomer first, okay. And then once you understand the enantiomer, okay, so following will be easy, okay, for the diastereomer, okay. So for the enantiomer, there are several types of enantiomers, okay. So first type of enantiomer we'll learn this here is kind of carbon with 4 different substitute, okay. 4 different substitute, okay. So 4 different attachment, okay. And then there's generally kind of this the carbon, okay, this molecule with the carbon with 4 different substitute, okay. With its kind of mirror imaging will become kind of the enantiomers, okay. Right. So for example, yeah, this molecule, okay, so mirror imaging to this molecule, okay, so that's the looks like kind of very similar to molecule, but here these two molecules act kind of non-superimposable, okay. Okay, so I make a model, okay. For example, yeah, these two molecules, okay, so yeah, they are mirror imaging to each other, okay. The white ball, blue, green, and also red, okay, match to each other, mirror imaging to each other, okay. But they are non-superimposable. They are two different molecules, okay. So yeah, so for example, okay, so I try to overlap these two molecules together, okay. So yeah, make this two green ball, superimposable, and this two blue ball blue ball kind of superimposable. But here the red and also the white one never can match each other, okay. So even sometimes I want to match the red one, okay, so red match to each other. Now kind of the blue and also the white one cannot match each other, non-superimposable. So that's the meaning of non-superimposable, okay. And so no matter how do you kind of rotate the molecule and then how to kind of rearrange the molecule, okay. So still cannot they are superimposable, okay. So not for all the 4 atoms, okay. So those 2 molecules, that should be 2 different molecules, okay. These 2 molecules we call the enantiomers, okay. Right. So enantiomer, okay, just keep in mind, okay, 2 kind of the conditions, okay. First, mirror imaging. Second, by kind of non-superimposable, okay. So enantiomer quite the kind of very general kind of in chemistry and also biology, okay. A lot of the molecule actually are enantiomer to each other, okay. For example, these 2, okay. So so this is the hydroxyl capsaicin, okay. So that's mirror imaging and also non-superimposable, okay. And actually organic molecule, okay, and biology molecule, okay. So more common for the enantiomer, okay. So L amino acid and also D amino acid actually kind of a pair of enantiomer. Mirror imaging non-superimposable, okay. And last example kind of a pair of limonene, okay. So those 2 actually kind of the only difference is kind of this carbon, okay. So this is carbon, okay. Mirror imaging, okay, this carbon has 4 different attachment, okay. Mirror imaging but non-superimposable, okay. And this pair of the enantiomer actually kind of our nose, okay, can sense them, okay. Our nose can tell difference, okay, so by their smells, okay, because our nose has a lot of the enzyme, okay. So enzyme actually kind of the enantiomer, okay. So can only bind one of the enantiomers, okay. That's why can give sense the different smells, okay. And the question comes kind of if we have 2 molecule kind of mirror imaging, but the superimposable, okay. So what's the relationship between these 2 molecules, okay? That's we call the identical, okay. All right, okay. So to further understand the enantiomer and also identical, so we do a little bit of practice here, okay. So I will draw 2 molecules, okay. So you guys tell me these 2 molecules are identical or enantiomer to each other. That's the wedge bond here. Right. Okay, so can anyone tell me these 2 molecules identical or enantiomer to each other? Okay, so these 2 molecules looks like a mirror imaging to each other. Okay. Anyone know the answer? Okay, so identical or enantiomer. Okay, someone said enantiomer. Okay, anyone have different opinion? All right. Okay. So the relationship between these 2 molecules should be identical, okay? Okay. The reason for that, okay, so these 2 molecules, okay, actually can same molecule, okay? So you rotate one molecule like 90 degree, okay? 90 degrees from enough, okay? You put the muscle here and then this muscle here, okay? That's exactly match here, okay? So that's we call the superimposable, okay? So that's here, okay? All right, so we try another 2, okay? And before the end of the class. So we have another pair of molecule mirror imaging to each other, okay? And then I draw you a last one, okay? Right, draw it mirror imaging, okay? Okay. Right. Okay, so we have two pairs of molecule, okay? So these two pairs, okay? Can anyone tell me kind of what's the relationship between these two compounds and also these two compounds? The top is the enantiomer or kind of identical, bottom enantiomer or identical, okay? All right, this time pretty good, okay? So all you guys kind of give right answer, okay? The top two will be identical, same thing to here, okay? So if you rotate one molecule 90 degrees, okay, exactly kind of match here, okay, that's identical, okay? But for the bottom two, okay, so will be enantiomer, okay? So no matter how do you kind of rotate the molecule and then kind of flip it, okay? So these two never match each other, okay? So non-superimposed, okay? So that's real enantiomer to each other, okay? All right, pretty good, okay? So you guys have a little bit of sense about the stereochemistry, okay? All right, so that's done the class today, okay? So if you have any questions, okay, so you can ask me now, okay? Yeah, I will go back to the definition of their theorem, okay? Don't worry about now, okay? So now you need focus on the enantiomer, okay? Enantiomer, okay? Yeah, have a good day, okay? So you too, thank you. Yeah, make sure you don't miss the Monday class, okay? So Monday class we'll talk some kind of most important kind of concept about stereochemistry, okay? Right. Have a good day, okay? All right. Lisa, do you have any questions?
No, sorry.
All right, that's fine, no problem, okay?